Keeper 6.1, Indefinite Integration. All right, so we have some common antiderivatives, and when I say antiderivatives, I'm talking about derivatives, like doing the derivatives backwards. So this first one is the power rule, and so if you remember the power rule, we drop the n in front, and we subtract 1 when we take the derivative, but when we do the integral, we do the opposite. So we add 1 to the numerator, and then, or to the exponent, and then we divide by that new exponent. So it's n plus 1 as the exponent over n plus 1. Now, all of these have this plus c afterwards, and that plus c is simply saying there could have been a constant that we took the derivative of, and it went to 0. So we're just saying we're holding a place for a possible constant. All right, the next few are your trig derivatives, and so I'll just read through a couple of them. The first one says derivative of sine was cosine. We learned that back when we did derivative rules. But now if I wanted to find the integral of cosine, that is going to be sine. Why? Because the derivative of sine is cosine. Or I could look at it as the derivative of cosine is negative sine. And again, we learned that back in derivative rules. So if I have the integral of sine, that's going to be negative cosine. Now the thing to remember here is every single time you get an answer that is C, or that has the letter C to start, your answer is going to be negative. So if your answer is if it's cosine, then you'll say negative cosine plus C. If your answer is cotangent, then you'll say negative cotangent plus C. And if your answer is cosecant, then you say negative cosecant plus C. So more common antiderivatives, or what we call integrals. The integral of 1 over x, if you remember, the derivative of ln x was 1 over x. So the integral of 1 over x is ln x. Now we have to make sure we put these absolute value signs here because we want to make sure that the argument for your ln is positive. The next one, we have integral of e to the x. And so again, if you remember, the derivative of e to the x was e to the x. So the integral of e to the x is e to the x. Again, adding on that plus c. You guys can read through the rest of them and write them down in your keeper. But it's pretty much you just have to recognize the derivative of the function so that you could tell what the antiderivative or the integral would be. All right, so your steps for solving these integrals, your step 1 is going to be rewrite. Step 2, you're going to integrate or find the antiderivative. And then step 3, you're going to simplify it, just like we did when we did like basic derivatives. All right, so example 1, we have integrate the following. Integral of 1 over x cubed dx. So first thing I'm going to do is rewrite this. I don't want it to be 1 over x cubed. I'd rather rewrite it as integral of x to the negative 3 dx. Once I rewrite this, I'm going to go ahead and integrate it. So I'm going to add 1 to my exponent and then divide by that new exponent. So I did negative 3 plus 1, and then I divided by that negative 3 plus 1. And again, you have to remember to add this c on here because there could have been some constant. Now I simplify, so I get x to the negative 2 over negative 2 plus c. And simplifying one more time, I'm going to have 1 over negative 2x squared plus c. Remember, we do not want negative exponents. All right, next example, we have integral of square root of x dx. And guys, remember, this dx is just notation. It's just telling us what variable to take the integral of. You're not actually taking the integral of dx. That's just your notation. All right, so we have integral of x to the 1/2 dx when I rewrite it. And then just like in the last problem, I'm going to add 1 to my exponent and divide by that new exponent. So I'm going to add 1 to 1/2 and then divide by 1/2 plus 1. And again, I add on that plus c to stand for any constant that could have been in the problem. Now when I simplify it, I get x to the 3/2 over 3/2 plus c. And I'm going to go ahead and flip my numerator, my denominator, so I don't have a double fraction. And so I have 2/3 x to the 3/2 plus c. All right, next example, we have integral of 1 over x dx. Now again, a lot of people will try to rewrite this as x to the negative 1 and they try to integrate it, but that would be incorrect because you'll get something that, you'll basically get something that goes completely away. What you have to remember is that when you see 1 over x, that was the derivative of ln x. So the integral of 1 over x is going to be ln x plus c, and technically, we should have absolute value bars here to indicate that that x should be positive. All right, so next example, we have integrate 13 over 17 e to the x. So the first thing I'm going to do is I'm going to pull that 13 over 17 out. I don't necessarily need it in my problem. It's just a constant, so I can pull it outside of the integral. Now, once I pull it outside of the integral, I realize that all I'm truly integrating is this integral e to the x dx. And again, we should know that since the derivative of e to the x is e to the x, then the integral of e to the x is e to the x. And so we have 13 over 17 e to the x, and then again, we always have to add that plus c. All right, next example, we have integral 2 pi sine x. Just like in the previous example, I'm going to pull out the 2 pi because it's just a coefficient. And so what I'm really focused on is this integral of sine x dx. And so the integral of sine, we have to ask ourselves what derivative would have given us sine. And so the derivative that would have given us sine would be negative cosine. So we have 2 pi negative cosine x plus c, and then just rewriting it to make it look a little better, I'd have negative 2 pi cosine x plus c. All right, so next example, we're doing an integral of x times square root of x. If I rewrite that, I get integral of 1 over x to the 3 halves if I add my exponents. And then I'm going to rewrite one more time to pull it up out of the denominator. So I have integral of x to the negative 3 halves dx. All right, so using my power rule, I'm going to add 1 to my numerator, or add 1 to my exponent in the numerator, and then divide by that new exponent. So I have x to the negative 3 halves plus 1 over negative 3 halves plus 1 plus c. And then cleaning that up, I get x to the negative 1 half over negative 1 half plus c. And then again, I'm going to keep change flip it so I don't have the double fraction. And I get negative 2 over x to the 1 half plus c, or I could have written that as negative 2 over root x plus c. Next example, we have the integral of 3 to the x dx. Again, using my formula from earlier slides, or just thinking about the derivative of 3 to the x. 3 to the x was 3 to the x ln 3. So the integral, instead of multiplying by ln 3, I'm going to divide by ln 3. So I end up getting 3 to the x over ln 3 plus c. All right, the next example, we have 1 over 2 x cubed. So the first thing I'm going to do is I'm going to rewrite it. But when I rewrite it, I need to recognize that the only thing I'm going to bring up is this x cubed. So it's going to stay 1 half, and then I'm going to bring up the x cubed. So I have integral of 1 half x to the negative 3 dx. Now rewriting it again, I can pull out that 1 half so that I'm only focused on the integral of x to the negative 3. And then using my power rule, I'm going to add 1 to the exponent, divide by that new exponent. So I have 1 half x to the negative 3 plus 1 over negative 3 plus 1 plus c. Simplifying that, I have 1 half x to the negative 2 over negative 2. And now getting rid of my negative exponent, I'm going to drop that x to the negative 2 back down. So I have negative 1/4 x squared plus c. All right, so this one's a very similar example to the last one, except this time the whole denominator is being cubed. So when I rewrite this, the first thing I'm going to do is distribute in my cubes. So I end up with 1 over 8x cubed. Now, just like the last problem, the only thing I'm pulling up is this x cubed. So I'm going to rewrite that as 1/8, and I went ahead and pulled it out of the integral, x to the negative 3 dx. So now all I'm focused on is taking the integral of this x to the negative 3. All right, so I add 1 to my exponent, divide by the new exponent, and then I simplify, and I end up with negative 1 over 16 x squared plus c. All right, the next one I need to, again, integrate this. The function looks a little crazy, but it does look like something that I've seen before. So if you remember your inverse trig function derivatives, you should recognize that this is just the derivative of sine inverse. And so the integral of 1 over square root of 1 minus x squared dx is simply sine inverse x plus c. All right, the next one we have the integral of x plus 3 times 3x minus 2. What I'm going to do is I'm going to go ahead and distribute this out. So I end up with 3x squared plus 7x minus 6 dx. And now I'm going to take the integral of each little piece. So for the first one, I'm going to add 1 to the exponent, divide by the new exponent. So I have 3x to the 2 plus 1 over 2 plus 1 plus 7x to the 1 plus 1 over 1 plus 1, and then minus 6x plus c. And simplifying that, we end up with x cubed plus 7x squared over 2 minus 6x plus c. All right, so the next example, we have a little bit of trig. And so the first thing I'm going to do is I'm going to go ahead and rewrite this used by splitting my denominators. In other words, taking that cosine squared and splitting it into cosine times cosine. So I have the integral of sine over cosine times the integral of 1 over cosine dx. Now, sine over cosine using my trig rules is just tan, and 1 over cosine is secant. And so now I have the integral of tan secant dx. And again, that should look familiar to you guys. You guys should recognize that that is simply the derivative of secant. So the derivative of secant is secant tan. Therefore, the integral of secant tan is simply secant x plus c. All right, so the last example, we have the integral of x squared plus x plus 1 root x. What I'm going to do is I'm going to divide and conquer this like I did with my derivatives. So I'm going to split it all up. So that's like x squared over root x over root x, and then 1 over root x. And then I'm going to subtract my exponents. So I end up with x to the 3 halves plus x to the 1 half plus x to the negative 1 half dx. Now using my power rule, I'm going to add 1 to all of those exponents and divide by the new exponent. So I get x to the 5 halves over 5 halves plus x to the 3 halves over 3 halves plus x to the 1 half over 1 half plus c. And then keep flipping it to make it look better. I'm going to end up with 2/5 x to the 5 halves plus 2/3 x to the 3 halves plus 2 x to the 1 half plus c.